Now coming to the part stresses in the rim flywheel, there are two main components. One is the arm and this arm. One is the arm and this is arm, and second is the rim. Now when flywheel rotates at high speed, large amount of centrifugal force acts on the rim, and due to this centrifugal force there are two stresses generated in the rim, that is one due to the force P, which is tensile force, so it generates tensile stress in the rim, and second is the moment in the rim, and so these two stresses will contribute in total stress in the rim. Secondly, now as the large amount of centrifugal force is acting on the rim, spokes are under tension because the rim will try to fly out, and this outward motion of the rim will be resisted by the arm, and now this arm will undergo a large amount of tensile stress. Say P1 is the load, so the tensile stress in the spoke can be computed as P1 by A1, where A1 is the cross-sectional area of the spoke. So by this formula we can compute the tensile stress in spoke. Now coming to the rim, already we have discussed that there are two stresses. One is the tangential stress and second is the bending stress. Now the resultant force is due to tangential stress and bending stress. So bending stress is computed as my by m, and for rectangular cross section, now rim have the rectangular cross section with b as the width of rim and t is the thickness of rim, we can say that y by I is equal to 6 by bt square, and area of the cross section of rim is nothing but equal to bt. Therefore sigma t comes to us as p by bt plus minus 6m by bt square. Now plus minus because half of the rim will undergo moment in compression. Now when it will bend, the inner part of the rim will go under elongation and the outer part will tend to compress. So it will have two types of stresses, so it is plus minus here. So here we this is the total resultant stress in the rim is nothing but due to the tensile load and due to bending load. Now these equations can be elaborated further. Now coming to the solution to the equation 1 and 2. Timoshenko have derived the equations to find out the value of P1, P and M, that is the bending moment. Before finding the solution, he had assumed some points, that is, first, the thickness of the rim is small in comparison to the mean radius, and stress due to bending moment and tension alone are taken into account. So we are going to consider only stress due to bending moment and tension alone. Second assumption was the length of the spoke is considered to be equal to mean radius, although in practice it is somewhat less than the mean radius. this assumption falls good, so nothing to worry about this assumption. So while finding the solution, he have found the solution P1 equal to 2 by 3 1000 mv square by c, where c is a constant and m is the mass of the rim and v is the peripheral velocity of the rim. C, the constant, have a value which is given by this equation, in which f2 alpha and f1 alpha are the new terms. Now f2 alpha and f1 alpha have been derived by this. Again, separate equations have been derived for f1 alpha and f2 alpha, where alpha is the angle between the consecutive spokes. So if we know the angle between the consecutive spokes, then we may find out the values of f1 alpha and f2 alpha. Now the second term in the stress developed in rim is the moment. So for m at angle phi, now this angle phi is measured from the vertical line in anti-clockwise direction. So for the angle phi, the moment at angle phi, the equation has been derived by the Timoshenko, and the moment equation is equal to 1000 P1 R upon 2, where P1 is the load, that is tangential load in spoke, and R is the radius of rim, and cos phi upon cos sin alpha minus 1 by alpha is the moment, and the value of P can be computed by this equation, where P1 is contributing, phi is contributing, and alpha is also going to contribute. So by putting these values in the previous equation, where we have find the stress in spoke and stress in rim, so stress in the spoke can be derived. We had already seen stress in the spoke is equal to P1 by A1. So value of P1 is already found here. So the equation of stress in spoke is given by this equation, that is 2 by 3 1000 mv square by c into A1. Now stress in the rim is computed by this equation. So this equation is nothing but the enlarged view of the previous equation, where we had taken the values of P, M into the previous equation, and this equation has been expanded. So these two equations becomes a lot of importance to find the stresses in spoke as well as stresses in rim. Now if a flywheel have 4 spokes, then angle 2 alpha becomes pi by 2, and therefore alpha becomes pi by 4. So at angle pi by 4, f1 alpha comes to us as 0.643, whereas f2 alpha comes to us as 0.00608. Therefore the value of C again can be computed as by this equation. So here the unknown terms are r square, that is T, R, A and A1, where R is the radius of rim, T is the thickness of rim, A is the cross section area of rim, whereas A1 is the cross section area of spoke. And when the rim have 6 spokes, then in that case angle 2 alpha becomes pi by 3, that is 60 degree, and therefore alpha becomes 30 degree. So for f1 t, that is f1 alpha, becomes 0.957, whereas f2 alpha comes to us as 0.00169 from these two equations. Therefore, the value of c can also be computed, and the equation again comes in terms of r, t, a and a1. So here we can find the equations in terms of r, t, a and a1. Now, as far as mass of the rim is concerned, we can compute the mass of the rim per millimeter of the circumference as m is equal to b into t into rho, where b and t are the width and thickness of the rim, and rho is the density of the material, mass density of the material. So these equations are of very much importance to find out the stresses in rimmed flywheel. Let us come to solve a problem on rim flywheel. In the problem number 1, it is given that the turning moment diagram of a multi-cylinder engine is drawn with a scale of 1 mm equal to 1 degree on the abscissa and 1 mm equal to 250 Newton meter on the ordinate. So on the ordinate, torque is given, and on the abscissa, angle turned by the crank is given. The intercept areas between the torque developed by the engine and the mean resistance torque of the machine taken in order from one end are. So from first end, it is been observed that the intercepted areas has been measured. So now these areas are measured. So the areas are in this manner. First is minus 350, so it is going down below the mean value, so it is minus 350, then plus 800, then minus 600, plus 900, minus 550, this is minus, then plus 450, then minus 650. The engine is running at a mean speed of 750 rpm, and the coefficient of speed fluctuation is limited to 0.02. A rim flywheel made of grey cast iron, grade of Fg200, that is density equal to 7100 kg per meter cube, is provided. The spokes, hub and shaft are assumed to contribute 10% of the required moment of inertia. The rim has rectangular cross section, and the ratio of the width to the thickness is 1.5. It is desired to determine the dimensions of the rim. Now it has been given to us the value of n, that is speed of engine, that is 750 rpm, speed of crankshaft, that is, then cs is the coefficient of fluctuation of speed, b by t ratio is 1.5, k is equal to 0.9, and as 10% only the area mass of hubs, shaft and spoke is going to contribute. So k becomes 0.9. Density of the material is given to us as 7100 kg per meter cube. Now the first part of the problem is to determine the energy output of the flywheel, that is U0. So energy output required from the flywheel has to be determined. So to derive the energy output, this T-theta diagram plays an important role. Already we have seen that these values are given to us in sequence. So if we take the stepwise energy storage in the flywheel, record of the energy storage in the flywheel, if let us say U is the internal energy which cannot be measured actually. So at point B, when it starts from A and comes to point B, let us say the energy becomes U minus. U was the initial energy in the flywheel, and then that is internal energy of the flywheel, and then at B it goes minus, so minus 350. So at point C it is U minus 350 plus 800, that is equal to U plus 450. Similarly at point D it comes to us as U plus 180. At point E it comes to us as U minus 150 plus 900, that is U plus 750. Now at the next step, that is at point F, we get the value of energy equal to U plus 750 minus 550. Similarly at point G it comes to us as U plus 650, and at point H we get the energy balance, that is equal to 0. Again, that is equal to actually U, not 0. So we see that the maximum and minimum energy occurs at point E. At point E, the total energy in the flywheel is maximum, that is U plus 750, and the minimum value of it is at point B, that is U minus 350. So at point B and at point E, there is maximum and minimum energy in the flywheel. Therefore, U naught is equal to UE minus UB, that is equal to nothing but 1100 mm square. Now this 1100 mm square, because it is been given that these values of energy is measured in mm square, so total fluctuation is in mm square. Now it is also been given that in the diagram the scale is 1 mm is equal to 250 Newton meter. So 1 mm on the abscissa, there is 1 mm is equal to 1 degree, and on the ordinate it is 1 mm is equal to 250. So total area is equal to 1 by 1 mm, that is 1 mm square. If we take, that is this 1 mm and this 1 mm, so total area 1 mm square contributes 250 Newton meter into degree. So now degree has to be, so it is 250, 1 mm is equal to 250 Newton meter, and 1 degree has to be converted into radian. So therefore pi by 180. So we multiply this 1100 by 250 into pi by 180. So we get the total fluctuation of energy in terms of Newton meter. So the value reaches us to 4799.66 Newton meter. So here the first step is complete, which is to find the maximum fluctuation of energy. Now this is the maximum fluctuation of energy in the given application. Accordingly, we need to find the dimensions of the rim. So the second step is to find the dimension of the rim. Now we know that the moment of inertia of flywheel is nothing but I, and moment of inertia of rim is nothing but IR. So moment of inertia of rim IR is equal to U naught K upon omega square CS. Now this formula is also given in the data book, and value of K is known to us as 0.9, and the value of U naught is already derived. Now value of omega can be computed as 2 pi n by 60, where n is the RPM of the shaft. So the RPM is also known, so omega can be drawn. So once we find the value of omega, CS is given to us as 0.002. Sorry, 0.02. So putting all these values in this equation, we get the value of moment of inertia, mass moment of inertia, which is required from the rim. So this is the mass moment of inertia which is required from the rim, that is 35 kg meter square. Now there is one restriction, that is the value of R should be such that the value of omega should not increase beyond certain limit. Now we know that the peripheral velocity should not increase 30 meter per second. Therefore, R into omega should be less than 30 meter per second. Therefore, we can say that R should be less than 30 by omega, and therefore putting the value of omega in terms of pi, 25 pi, we get R is equal to 0.3, R should be less than 0.38 meter. So assuming that the value of R equal to 0.035 meter, we can compute IR is equal to mr square, where R is the mean radius, and mean radius we have assumed it as 0.35 meter. Therefore, mass of the rim is equal to IR upon R square. So IR is nothing but 35 kg meter square upon 0.35 meter square is equal to 285.71 kg. So mass of the rim comes to us as 285.71 kg. Now radius of the rim is fixed, and we want to have this mass on the rim, so we need to find the other two dimensions, that is T and B. Now mass of the rim is equal to 2 pi r, that this 2 pi r is nothing but the length of the rim, that is nothing but circumference, right? So this circumference into B into T. Now B is in mm, so we divide it by 1000, T also we divide it by 1000. So this total is nothing but the volume of the rim into the density. Now we have been given that B by T is equal to 1.5. Therefore, we put the value of B is equal to 1.5 T. Therefore, putting the value of B equal to 1.5 T, we get the value of T equal to 110 mm, and as we get the value of T is equal to 110 mm, B can be computed as 1.5 T, and that is nothing but 165.67 mm. Therefore, for this particular case, the radius of the rim is nothing but equal to 0.35 meter, that is 350 mm, and thickness of the rim is equal to 110 mm, and width of the rim is 170 mm. So in this way we finalize here the dimensions of the flywheel for the given application. Let's move to the next problem. In previous problem we had solved the given condition in order to find the dimensions of the arm flywheel. Now in the second problem we will try to find the stresses in arm and rim of the flywheel. Now the given data is as follows. The following data is shown for the rim flywheel is given when the flywheel is made of grey cast iron. Now The grade of the grey cast iron is given to us as Fg200. Now mean radius of the rim is 1.5 meter, thickness of the rim is 200 meter, width of the rim is 300 mm, number of spokes is 6, cross sectional area of each spoke is 10,000 mm square, so there is no need to find the area of the area of the spoke. Then width and thickness of the rim is also given to us. Speed of rotation is 720 rpm. Calculate the tensile stress in rim at phi equal to 30 degree and phi equal to 0 degree. Second, it is desired to find the axial stress in each spoke. The mass density of cast iron grade Fg200 is 7100 kg per meter cube. Now, as per the given data, the value of n is given to us as 720 rpm. Radius of rim r is equal to 1.5 meter. Thickness of the rim is equal to 200 mm. T denoted by T. Width, that is B of the rim, is equal to 300 mm. For spokes, A1, that is area, is equal to 10,000 mm square. Number of spokes is equal to 6, and density of the material given to us as 7100 kg per meter cube. Now, first step to find the tensile stress in the rim. Now, we know that there are two elements which have the maximum stress, that is, one is the rim and second is the arm. As far as hub is considered, hub do not have that much amount of stress compared to rim and arm. Hence, it is important to find the stresses in rim and arm only. So, as far as stresses in rim is considered, there are two types of stresses. One is tensile stress and second is bending stress. Now, the total stress in the rim is the combination of tensile stress and bending stress. So, total stress sigma T in the rim is given by this formula, and this formula is already given in data book. So, it is 1000 mv square by Bt into 1 minus cos phi upon 2 sec sin alpha plus minus 2 into 1000 r by Ct into 1 by alpha minus cos phi upon sin alpha bracket close, and here there is a second bracket. Now, if we see this formula, there is plus and minus sign. So, plus and minus sign indicates the stress due to bending moment. Now, already we have discussed in the previous section that this bending moment generates two types of stresses. One is compressive stress and second is tensile stress. Now, when we measure the stress on the rim where arm is attached, in that case this rim cannot move away from the center of rotation, whereas the part where arm is not there, that part will tend to move away, bend. So, due to this, at this particular position of the arm, it will have purely tensile stress, because this rim will tend to move like this, right? If I take another, that is pen here, then this rim will tend to move like this, and this will generate a tensile stress at the rim at the position where arm is attached. This arm is there, and this where this arm is attached, this rim will tend to move in this way, and due to this there will be tensile stress in the rim. And the point here, when it is there is no rim, so there is no rim here, so at this position it will have a tendency to move like this, and this tendency of the rim will tend it to compress at this section, because the lower it will try to compress and it will exert a compressive load. So whenever we will calculate this stress, it becomes important to measure the angle phi. This angle phi is very much important, and it has to be measured positive in anti-clockwise direction. So this direction is also important. So when so theta phi is measured 0 at this position, and the angle phi is measured positive in anti-clockwise direction. Now as we have the angle, the number of spokes equal to 6, the subtended angle 2 alpha is equal to 60 degree, and this angle alpha will become 30 degrees. So it has been said here to find the stress at angle 0 and at angle 30 degree. So it is important to measure stresses in rim where arm is attached and where arm is not attached. So these two, we are interested to find the stress at these 2 points. Now continuing the section, here already this formula is known to us, and by going through this formula, we see that we have the value of B and T, but we do not have the value of M, V. Then alpha is also known, that is 30 degree. Phi is as per requirement, so if we compute the stress at phi is equal to 30, then we will put phi equal to 30 here in this formula. Then capital R is also known. C is not known because C is the constant, and that has to be found. Okay, so first let us find the value of M. So M is equal to BT into density, that is the mass per unit length of the rim. Therefore B is given to us as 300, T is given to us as 200 and mm, and putting these values in, already density is also given in meter cube. So converting this into mm cube, we will get 7100 10 to the power minus 9 mm kg per mm cube, and therefore mass of the rim per unit length, or mass of the rim per unit area, is equal to 426. So here we compute the mass of the rim. By multiplying the radius of the rim, we will get complete mass. Then area is equal to BT. Then now C, if we see the formula for constant C, it is 20 to 80 R square by T square plus 0.957 plus A by A1, where A is the area of rim while A1 is the area of cross section area, that is arm. Therefore, by putting now already we know the value of A, we know the value of A1, we know the value of R, and we also know the value of T. Therefore, putting these values we get the value of C equal to 8.098. Now already we have found the value of M, value of V is not known, so V has to be found. Therefore, V is equal to omega into R, and that is equal to 2 pi n by 60 into R. Putting the value of N in and R in this equation, we get the value of V in meter per second. Therefore, now alpha, we can separately find the value of this as this particular part of the equation, and that putting the value of mvbt we get the value of this particular term. So it comes to us, that is 1000 mv square by bt comes to us as 90.816. Now 2 alpha is equal to 360 by 6, that is number of spokes. Therefore we get alpha is equal to 30 degree, and by putting the value of phi is equal to 30 degree, we can find the value of sigma t. Now when we find the value of sigma t, we understood that this equation we use positive sign to find the stress when at the position on the rim where arm is attached. So using this positive term and putting the value of cos phi, sin alpha, c, r, ct, all these terms are known to us now. So sigma t is computed as 114.25 Newton per mm square. So using positive sign because it is at the position of the rim. Now where position of the arm, now the stress at the position where there is no arm, that is phi is equal to 0 degree. So phi is equal to 0 degree if we put, then we will use negative sign, and the term can sigma t, that is stress on the rim at phi is equal to 0 degree, comes to us as 98.5 Newton per mm square. Now axial stress in the spoke. From the equation 21.17, the stress in the spoke is given by, now this equation number is printed from the book itself. So from the data book we will get this formula for stress in the rim. The equation number may change, but the same formula is available in the data book. So sigma t in the for the rim, for the arm can be computed as 2 by 3 1000 mv square by CA1. So constant C is known to us, A1, that is the area of cross section of arm, is also known to us. So putting these values in this equation, we will get stress in the arm equal to 44.86. So in this way, if in any problem, if it is asked to find the stress in the rim and arm, we can compute the values of stress and arm by means of these formulae available in the data book. Already we have discussed in detail the significance of these formulae. So here we complete chapter number 4, unit number 4, and the chapter design of flywheel. Thank you.